Alright, I'm going to go over the solutions to a couple of these problems, a few that might have been a little more confusing that you haven't seen before. So make sure you take a look at them if you were confused in any way. Okay, so for problem number 2, I want to construct a rectangular plot of farmland. It's bounded on one side by a river here, and you have a total of 900 meters, maybe it's slightly different for your problem, 900 meters of wire with which to use. And you want to know what is the largest area you can enclose and what are the dimensions. So we're trying to maximize area, and so we're going to need to write an equation that represents the area of this plot of land. And then we'll need to maximize it and find those particular dimensions that make that area maximum. Okay, so I've drawn my picture here and I want to label with key components. So there's a couple of things that I need to recognize. I want to write an equation for the area, and I want it to be in terms of the thing that I can control. Well, what I can do is I can control the lengths and or I guess we'll call this the length, and the widths of my farmland. So I want to give those variable names. So let's start with the two widths here. They're going to be the same, and let's just call each of those x. Now, you might be saying to yourself, well, how do I know what variable name to give the length here? Because it's clearly this length is different than the widths. But remember, they are related. So if at first you were to give it a different variable name, let's just call it y for a second. And you're then going to try and write an equation for the area. Well, clearly the area of this plot of land is x times y. But you know that you need to write that equation in terms of one variable. So let's just start out with that. Our equation at first will be area is equal to x times y. But that doesn't quite encapsulate all the information we have, because what we're told is that the amount of wire fence that we have is 900 meters. So let's think about this very briefly. If you control the two widths and make each of those side lengths x, what does the side length y have to be? Well, obviously you're going to want to make it as long as possible. So you're going to take all of the 900 meters of wire that you have, you're going to subtract away the two widths, and whatever you have left over is going to be your length. So in other words, it would be 900 minus 2 of these x's. And we can represent that with an equation. So what we know is that 2x plus y is equal to 900. So when you're trying to write an equation for y in terms of x, so that you can represent this whole equation in terms of x, what you'll end up with is that y is equal to 900 minus 2x. And what I would do is actually just write this right off the bat. So as I'm filling out my dimensions, I would say to myself, well, I know that I need this length in terms of x, because the length times the width is going to be the area. So if I have a total of 900 meters of wire, and I've already chosen that each of the widths be x meters, what's left over? Well, it's going to be 900 minus 2x meters. So now rewriting my equation for the area, and I would have done this as in my first equation if I had thought this process through and labeled the side lengths as such. I would have x times 900 minus 2x. Now, if I'm following the strategy that I've outlined for optimization problems, the next thing I want to do is make sure I understand what the domain of this function is going to be. In other words, what are the values of x that are allowable in my construction of the farm, and then take a look at the graph. And there's a couple things you'll notice. Obviously, if 900 minus 2x is 0, that would be the absolute lowest it could ever be. I mean, you'd have a very weird looking plot of farmland, but you obviously don't want this to be negative. In other words, you cannot make 2x bigger than 900, which means you can't make x bigger than 450. It would also not make sense for x to be anything less than 0, because then you'd have widths that are less than 0, and that doesn't make sense for area. So you're going to go between 0 and 450. And that should be pretty clear, especially when you take a look at the graph. So now taking a look at the graph, you can probably identify pretty quickly where the absolute maximum is going to be, and then take a look algebraically and find that on your own. I'm going to sort of skip ahead through these portions so that the video is a little more streamlined. Okay, so taking a look at the graph of the area in terms of x, you can see that the maximum is pretty clearly occurring what appears to be around 220-ish, 225 as the value of x that makes this a maximum. And when I go ahead and find the derivative, what I did was I distributed the x in first so that I could use the power rule, and I get a derivative of 900 minus 4x. Setting that equal to 0 to find the critical points, I get an x value of 225, which makes a great deal of sense. I do need to check the endpoints along with the critical points, but that shouldn't be too big of an issue. So when I make my table of values for my critical points and my endpoints, it'll be pretty clear which one is going to be the absolute max. And when I go through and I test the endpoints and the critical points, I can clearly see that the maximum value occurs when x is 225 meters, and that will give me a maximum area of 101,250 meters squared. So you need to make sure that when you are writing your answer, that you're saying the maximum area is 101,250 meters squared, and you also want to include the dimensions at which this occurs. And so this occurs when x, which is the width of your farmland, is 225. So the width will be 225, and that leaves the length to be 900 minus 2 times 225. 225 times 225 is 450, so that will leave you with a length of 450. And so you can say that this maximum area occurs when the farmland is 225 meters by 450 meters. Alright, here for number 3, I'm going to find the smallest perimeter. So I'm looking for the absolute minimum value of the perimeter of a rectangle. And here's my rectangle, where I have a width and a length. And I know that the area is 25, which means the width times the length is 25 inches squared. And I want to minimize the perimeter. So the perimeter is the function I want to write, or what I want to write a function for. And I know that perimeter is going to be equal to x plus x, or 2x, plus y, or 2y. But remember, I can't maximize a function unless it's in terms of one variable. So I want to rewrite y in terms of x. And luckily I have a relationship between x and y, which is that when you multiply them together, you get 25, because that's the area of the interior. So solving here for y, I get that y is 25 over x. And so that allows me to write my perimeter in terms of x, and now I will have a function that I can minimize. As such. Okay, so there's a couple things to note. The domain here is going to be all x values greater than 0. Notice that if I had an x value that were 0, then the area would be undefined here, and so that won't work at all. And so notice there are no endpoints, right? I don't have a defined left endpoint or right endpoint. I go through and I find the derivative. I multiplied 2 by 25, that gave me 50. So it was 50 times x to the negative 1, took the derivative of that, and that got me negative 50 over x squared. I want to find where the derivative is equal to 0, and it will be equal to 0 when x is equal to 5. Now remember, that's not the only critical point. I could have a critical point when the derivative is undefined, and the derivative would be undefined when x is equal to 0. However, that's not in my domain, so I don't need to worry about that critical point. It's not going to be a potential absolute minimum. So if you looked at the graph, which I didn't bother to go through, but if you looked at the graph of the perimeter here, it would be pretty clear that the minimum value occurs around when x is equal to 5, and so it appears that we're on the right track here. I would use the first derivative test because I don't have any endpoints here, so I'm not going to use the closed interval test, and I don't want to find the second derivative. So what I will do is I will make a sign chart for the derivative of my perimeter. My critical point occurs when x is equal to 5. That's where the derivative of p is 0. And then testing values to the left and to the right of 5. We'll see that if I, for example, easy one is if I input 1 for x, I have 2 minus. Now 50 divided by 1 squared is 50. So 2 minus 50, that'll clearly be negative. So that means here that the perimeter is decreasing, right? Meaning the value of the perimeter is decreasing. I'll write that here. P is decreasing. All right, and to the right of 5, perhaps if you plug in something like 6, you'll see that the derivative is positive, and this means that the perimeter is increasing. And we know, of course, by our first derivative test that if the derivative goes from negative to positive at a critical point, then at that critical point we have a minimum. And since this is our only critical point, we know that this is where the absolute minimum occurs. So at this critical point, when x is equal to 5, we will have an absolute minimum for our perimeter. So now we can answer the question. We can find what the perimeter is when x is equal to 5. So P of 5, and here I can pretty clearly, I'm going to have 2 times 5, so I'll have 10 plus 25 divided by 5 is 5, so I'll have another 2 times 5, which is 10, and that will give me 20. And here I have inches. So the perimeter will be at a minimum when the width is 5. Also, this means, so x will be equal to 5 inches. And if you then find what y is 25 divided by x, so y is also going to be 5. In other words, this will have a minimum when this rectangle is a square. So the perimeter will be at a minimum value of 20 inches around when both the x and the y values, or the length and the width of my rectangle, are 5 inches. Alright, so here's the setup for number 6. This problem takes a little while, but I'm going to kind of go through the most important steps and discuss some of the intricacies a little bit. But if you trust your process here, you'll be just fine. So I've drawn my semicircle. It goes from -4 to 4. I've drawn the point P, which is the point 1 comma square root of 3. And the goal of the question is to find where the semicircle comes closest to this point P. So based on that, I know that I'm trying to find the minimum value of the distance between any point on my semicircle and my point P. So what I'll need to do is I'll need to write a function for the distance, or as we've seen previously, we can write a function for the distance squared, and then find the absolute minimum of that function, and that will tell us where the point along our semicircle is that is closest to this point P. So I need to represent the distance between any point on my semicircle and this point P in terms of the variable that I am able to control, which is of course the x value of my coordinate along my semicircle. And of course the x value will tell me also the y value because I have the function defined. Now, just looking at the picture that I've drawn, since I've drawn it fairly accurately, it's pretty easy to tell that the points that are going to be closest to this point P are not going to be over here between 0 and -4. But I can still write a general equation for the distance between this point and any point on my semicircle. But just to make it more visually correct, let's go ahead and write our point, our general point, as some point on our semicircle in the first quadrant. Okay? So what are the coordinates of this point here? Well, the x-coordinate is just the x-coordinate, and the y-coordinate is given by the square root of 16 minus x squared, right? That's how I find the y-coordinate. All right, so that point there is given by x comma square root of 16 minus x squared. Those are the x and the y coordinates. And now what I want to find is the length of the segment that connects those 2 points. And we'll call that the distance. Okay. Now, our strategy for finding the distance of a line segment is to construct a right triangle that involves that line segment as one of its side lengths. And then we can use the Pythagorean theorem to write a function for that line segment's distance squared. And it's going to be very helpful if we can think about the other side lengths of the right triangle in terms of x, right? We're going to need to be able to calculate those values in terms of what x is. And so it'd be very helpful if both of those side lengths are either perfectly horizontal or perfectly vertical. There's actually kind of 2 ways I could draw this triangle. I could draw it like this. I could draw it like this. Really, either way is going to work just fine because I'm going to be squaring the side lengths anyways, so it really doesn't matter. Let's go ahead and just draw it kind of right side up like that. Alright, so what I'm going to do is I'm going to enlarge this triangle here so that we can clearly see and write down what each of these side lengths is going to be. So here's my triangle. Now let's first think about the horizontal distance. So the horizontal distance is going to be the horizontal distance between these 2 points. Well, this point here has a horizontal value, an x value of x, and this has an x value of 1. So the distance between these 2 points horizontally is going to be x minus 1. Alright, what about the vertical distance? Well, the vertical distance between these 2 points is going to be the vertical distance of this point minus the vertical distance of this point. So it's going to be the square root of 16 minus x squared minus the square root of 3. Now, notice that we've constructed both of these side lengths in terms of x. So when I use the Pythagorean theorem, I can write a function for the distance squared in terms of each of these side lengths squared. And so these are both in terms of x. That's just wonderful. That's what I want. Now there's one thing that you might notice, and that is this. If you were to take this point, and let's say you took your point and you were somewhere over here, you know that's not going to be where your distance is closest, but let's just pretend it was over there. So your distance is the length of this line segment here, and you would construct your side lengths of your right triangle like this. Now, you know that the x value of this coordinate here is something less than 1. You know, say it was like -1. So when you're finding the distance, it would be -1 minus 1, which is -2. And that's actually the opposite of the true distance here, right? Length is always in positive value, and if this is -1, this is +1, that distance is 2. And you're like, maybe that's a problem. But recognize that the Pythagorean theorem means that we're going to square both these side lengths. So even though I would get a -2 using this computation, x minus 1, when I square it, I'm going to get a +4, which is the same as what I would get if I had 2 squared. And the same can be true for this y distance here. For example, if I had a coordinate point, let's take some coordinate point down here. Notice that if the point on my semicircle were down here, then the y distance that I would get, the vertical side length, would be negative according to this construction. But when I square it, it's going to revert to the positive value that I need. So the Pythagorean theorem luckily takes care of all of those situations, and I can remain steadfast in my representation in the original way that I constructed it. So now I can write a function for the distance squared in terms of these 2 side lengths. So there's my function for the distance squared. Now if I wanted to find a function for the distance, I'd have to square root this whole thing. But remember, I am going to take the derivative, and I would like to take the derivative of as simple a function as possible. And so notice that if I just keep it as the distance squared and I minimize the point, minimize a function for the distance squared, I'll be finding where the square of the distance is smallest. Well, where the square of the distance is smallest is also where the actual distance is going to be smallest. I'll just need to take the square root of that value that I get to find the true distance. So we'll let this be the function that we are going to minimize. This will be a function f of x. and it will be this thing right here. Now, I want to think about the domain of the function, and I want to take a look at the graph of the function to help me visualize it. That's going to be very key here. So thinking about the domain, what are the x values that are appropriate here? Well, just looking at my semicircle, I see that I can go from -4 to +4, and I can include those points, right? Both of those points work just fine. So our domain for our function is going to be all x values between -4 and +4. So now you can take a look at the graph of this function of the distance squared in between these two values, and you can see where you think the minimum value is going to occur. So there's the graph of the function f of x, which represents the distance squared, and you can see pretty clearly here that the minimum value appears to occur right there when x is +2. So you know what you're looking for, now you need to go find it, and in order to do that we're going to take the derivative of this function, find the critical points, and evaluate the function at the endpoints and the critical points. So I'm going to kind of go through this sort of quickly and write it out and then kind of explain it. You want to be careful with this derivative of this piece here. You're going to need to use the chain rule 3 times. But if you take your time and do some scratch work to the side, you'll be a-okay. Alright, so taking the derivative, the chain rule 3 times, I have this function here squared. So I take the derivative of the outside, keep the inside the same, raise to the first power. Notice I just didn't write this here to save space. Then I've got to take the derivative of this inside function. So I have to take the derivative of these two square roots, the difference of these two square roots, that's the green part. The derivative of the square root of 3 is 0, so I don't need to worry about that. Take the derivative of this square root here. Now to take the derivative of this square root, I again use the chain rule. I have this function here square rooted. So I take the derivative of the outside, which is just this function square rooted, so it's 1/2 times the square root of this function. And then I need to take the derivative of the inside piece, which is 16 minus x squared. Derivative of 16 is 0, derivative of negative x squared is negative 2x. I guess one key to remember here is that when you're taking the derivative of a square root, you can think of it as being something raised to the 1/2, and that will allow you to see where you get this from. Now I'm just going to go ahead and simplify. Alright, so there's the simplification. Notice what I did is I canceled those 2's out. So then I have this square root, which is 16 minus x squared, minus this square root of 3, times all of this. So I have to distribute. So I have negative 2x over this square root times this square root. Now these are the same square roots, so those cancel out, and I'm left with negative 2x, which is right here. And then I have negative 2x over this square root times negative square root of 3. So a negative times a negative becomes a positive, so I have positive 2 square root of 3 times x over this square root here. I have a positive 2x from this multiplication, so those 2x's will cancel. I'll be left with negative 2 plus this, so I just swapped the order. And I'd factored out a 2 because there's a 2 here and a 2 here. So it'll become 2 times square root of 3 times x over the square root of 16 minus x squared minus 1. That is my derivative. Okay. So now what I want to do is I want to set the derivative equal to 0. Now, setting this equal to 0 means that I have this in factored form, right? And then at 2 is never going to be equal to 0. So the only way that this function can be equal to 0 is when this piece here equals 0. So setting this equal to 0 and then adding 1 to both sides, I'm going to have this rational expression equal to 1. So f prime of x will equal 0 when this rational expression equals 1. Then multiplying by the square root in the denominator on both sides, I will have square root of 3 times x equals square root of 16 minus x squared. That's where I'll start off. Okay, at this point, you're hoping, of course, that this works out when x is equal to 2. Now you could try that and see if that works out for you. But we can solve this for x rather simply. There's just one thing that we need to take note of. What we're going to need to do is unlock this x here. So we'll need to square both sides. Now when you square both sides, be careful, because squaring both sides, as we discussed in last year's course, Squaring both sides takes all positive values and all negative values, and when you square them, it can't tell the difference. So you need to take note of this equation here. This side will always be positive, right? Because we're going from -4 to +4. But this side here will potentially be negative. So you can never have a negative be equal to a positive. So this equation will only be true when x is a positive value. So in the back of your mind here, you're thinking for x greater than or equal to 0. So when you solve this equation, you only want to consider x values that are greater than or equal to 0. So going through and squaring both sides will give me 3x squared is equal to 16 minus x squared. Now, collecting all of the terms on one side, because I notice I'm going to have a quadratic here, and that will allow me to set the quadratic equal to 0, I'll end up adding x squared to both sides. That'll give me 4x squared, and subtracting 16 will give me 4x squared minus 16. So factoring out of 4 will give me 4 times x squared minus 4 equals 0. And I can solve this easily, because what will make x squared minus 4 equal to 0 is when x is either -2 or +2. So that you'd be tempted to write down that you have two solutions, but this is only when x is greater than or equal to 0. So the only x value that you can take away from this solution is x equals +2. That is in fact the only critical point that you can take away. So now, testing your closed interval test, you have the two endpoints, -4 and +4, and the critical point, x equals 2. All right, so here is my table for my closed interval test. I tested both the endpoints, and I plugged them in, right, to my function that gives me distance squared, right? F of x gives me the distance squared. So I'd get 28, but I want the distance, the square root of 28. I know that's a little more than 5. When I plug in a value of 2, right, so if I think about the x value, that dictates where my point on my semicircle is. So -4 would be over here. Clearly, that's going to be a little far away. 2 is probably somewhere around here. And when I take the distance squared at an x value of 2, I get 4. So I take the square root to find the actual distance, and that's 2. And then at an x value of 4, so where I'm at this point here on my semicircle, I get a distance squared of 12, and the square root of that is going to be in between 3 and 4. So clearly the minimum occurs, the absolute minimum occurs when x is 2, and the distance between the point on my semicircle when x is 2 and the point P is going to be 2. That's the actual distance. What is this point on your semicircle? Where the x value is 2, and the y value is going to be 16 minus 4, because x is 2, square root of that. And so that's going to be the square root of 12, which again is a little between 3 and 4. All right, hopefully that was helpful, and be sure to look out for video 5.04 coming up soon.